Alright, so we have another example here. Um, a mass oscillating in simple harmonic motion starts at 6.9 meters and has a period of 2.6 seconds. At what time does the object first pass through half the amplitude? So half the value of the amplitude. So for this, you should assume that amplitude equals 6.9 meters. And because x equals 6.9 meters at t equals 0, therefore the phase constant has to be 0 radians. So that's the assumption that we have to make. So now we just plug in our 1/2 a to the equation. So when x equals 1/2 a, and we're trying to solve for time, so a cosine omega t plus phi. The a's cancel out, so you get 1/2 cosine omega t plus phi equals omega. So now we're going to take the inverse cosine of both sides. So we get the inverse cosine of 1/2 is just pi over 3. And then you get w t plus phi. We know that phi is 0, so it's just pi over 3 equals omega times t. And then you get that t equals pi over 3 omega. So omega is 2 pi times t. So we get t equals, or 2 pi times f, my bad. So we get pi over 3 times 2 pi f. Those cancel out. So you get equals pi, or no pi, sorry. So you get 1 over 6f. Or you get t over 6, because t is equal to 1 over frequency. So when you do that, you should get a time of about 0.43 seconds. So here we have a spring with a period of 0.81 seconds and an amplitude of 10.18 seconds. 10.18 centimeters. And then when it starts out, it's 4.2 centimeters to the left of the equilibrium moving to the left. So basically, we have to find the position and velocity at 2.01 seconds. So first of all, what I think is important is to find the phase constant. So let me just draw something. Let's just draw like a line. So we have negative a, and 0. So right here, the object is right here at 4.2 centimeters, and it's moving to the left. So what I'm gonna do is I'm gonna draw a circle out of this number line. Sorry if this is not straight. And basically have a tangential speed at every point on the circle. And we're moving counterclockwise since that's considered positive. So and then this is the y-axis. So this is the y-axis right here, and then this is the x-axis. So this is starting to look like a coordinate plane, right? So knowing from this coordinate plane, we know that it is either in quadrant 2 or in quadrant 3. So the way to figure out where it is um, basically you have to look at its speed. So the tangential speed um, right here, or the speed right here is moving to the left. So we have to look for if quadrant 2 or quadrant 3 looks like it has the tangential speed on its edge that's moving to the left. Well, right here, you see these arrows pointing to the right, but you see right here, the arrows are pointing to the left. Thus, um, our phase constant has to be in um, basically it has to be in quadrant 2 because it's moving to the left, and that's where the arrows are pointing, and it's also the left of equilibrium. So let's just try to solve the phase constant right now. But we have to be aware of what quadrant it's in. So negative 4.2 equals 10.18 times the cosine of v, because when you at t equals 0, it doesn't really matter about the angular frequency because it just cancels. So we get the arc cosine of negative 4.2 over 10.18, and that equals 1.996 radians. And the reason why it's negative is because it's left the equilibrium. Now, the thing is, the arc cosine is basically truncated because it has to be a 1-to-1 function. So if we do 0 to 2 pi of, say, the arc cosine function, it would look something like this. But we have to make sure it's a 1-to-1 function, so basically split it in halves. So we can do 0 to pi, or negative pi to pi, or as long as, or no, not negative pi to pi, negative pi to 0, or pi to 2 pi, however see fit. But in this problem, we had to use negative pi to 0. And also, this is not just 1.9996 rads, it's plus or minus, because remember, cosine is a even function, so plus or minus, or let me just rewrite it, so plus or minus 1.996 rads, because cosine of x equals cosine of negative x. So could it be either one? But in this case, we have to follow one of these domains. But for this problem, we have to use negative pi to 0. So the phase constant that we're using this time is negative 1.996 radians. So now we can solve for the position at 2.01 seconds. So we get x at 2.01 times the amplitude, 10.18, times cosine, and then now the period matters. So it would be 2 pi over 0.81, right? Because 2 pi f, so w, so like omega equals 2 pi f, but since frequency and period are reciprocals, it would be w equals 2 pi f, 2 pi over t. And then times 2.01, and then plus negative 1.996. So when you plug everything in, you should get about 5.248 centimeters. So now we could either do one or two things. We could either use conservation of energy, or we can solve it with calculus. But I'm going to personally use conservation of energy. So the position, so we know the position at 2.01. So that's right here. So at t equals 2.01. And we know that, but we need to find the velocity at 2.01. So find v. So t equals 1. Well, we are given the amplitude. So we can use the maximum potential energy as the total energy, which is, and energy is always conserved. So the sum of x of the position of the potential energy at 2.01 and the kinetic energy at 2.01. When you sum them up, they should equal the maximum potential energy or the total energy. So we're gonna isolate v. So we get 1/2 ka squared minus 1/2 kx squared equals 1/2 mv squared. So ka squared minus kx squared equals 1/2 mv squared. Distribute the k, factor out the k. A squared minus x squared equals mv squared. Divide by m. K over m is a squared minus x squared, and then equals v squared. And then this is the same thing as omega squared. And then v just equals omega times the rad of a squared minus x squared. So we already know the amplitude. So we already know the amplitude, which is 10.18. So, and we already know the angular frequency, which is 2 pi over 0.181. And then times the square root of 10.18 squared. And then the thing is, we already calculated this, so it would be 5.25 squared. So when you calculate all of that, you should get a value. Here, let me clear space. So v equals 2 pi over 0.81 times the square root of 10.18 squared minus 5.248 squared. So when you solve all of that, you should get an answer of 67.6668 centimeters per second.